Hey guys, Miss Gosling here. In this video, you are going to learn about half-life. By the end of the video, you will be able to solve half-life problems. So let's go ahead and get started by talking about what a half-life is. So a half-life is the time it takes for half of a sample of an isotope to undergo nuclear decay. So what does that actually mean? So on the left-hand side of my screen, I have a sample of carbon-14 atoms, which are unstable. So these carbon-14 atoms, represented in purple, aren't going to stay carbon-14 atoms forever. Instead, what I'm going to observe happening over time is some of my carbon-14 atoms are going to decay into nitrogen-14. So at the beginning of my initial sample, what I have here is I have 12 carbon-14 atoms. Once one half-life has elapsed, half of those atoms are going to decay into nitrogen-14, represented by those little orange circles. So instead of having 12 carbon-14 atoms, I'm going to have 6 carbon atoms and 6 nitrogen atoms. After another half-life has elapsed, another half of my carbon atoms are going to decay. So now instead of having 6 carbon atoms, I'll have 3. So how many do you think I'll have after 3 half-lives? That's right, I'll probably have either 1 or 2, since what I would assume is 1.5, but of course I can't have half an atom. Now, one thing that's really important to know about half-life is that half-life is a probability. So what that means is that half-life is kind of like flipping a coin. After one half-life has elapsed, any single atom has a 50% chance of having flipped, or having decayed, just like I have a 50% chance of flipping tails with a coin. What that means, though, is if I look at a single atom, I'm not going to find that that single atom has decayed halfway over one half-life. Instead, what I would expect is that if I had 2 atoms, one of them would decay and one wouldn't decay, because there's a 50% chance, again, of an atom decaying in that time. Kind of like, but also if I only have 2 atoms, there's a decent chance both decay. There's a decent chance that neither decay. Just like if I flip 2 coins, yeah, most likely I'll get 1 heads and 1 tails down here, but there's a perfectly decent chance that I end up with 2 tails, 2 decays, or 2 heads, 0 decays. So when I'm talking about nuclear decay, it's really important that you guys are aware that we are dealing with huge samples of atoms. For example, if I have 55.84, let's say 55 grams of iron, what that means is I have 1 mole of iron, or 1.602 times 10 to the 23rd atoms. That, of course, is a lot more than 2 atoms, or 2 coins. And so when I'm looking at numbers of atoms on that scale, it's very, very likely that I am going to see that half-life equation play out perfectly, where half of my atoms decay after one half-life has elapsed, and another quarter decay after the next half-life, another eighth after the third, and so on. So again, just keep in mind when we're doing this, we're looking at very large numbers. Now, how we measure half-life is using a tool called a Geiger counter, which you can see pictured here on the right. The Geiger counter measures radioactive activity by doing the following. So first, it's going to just measure the background count, because there is always nuclear decay happening all around us. So that Geiger counter is going to measure how much nuclear decay is just happening in the environment. Then what I'm going to do is say, okay, so what's the decay rate when I hold this right over my sample? And when I subtract the sample count rate from the background count rate, what I'll get is I will get the amount of radioactivity going on within just my sample. So with that, let's go ahead and take a moment to do a couple of examples. So first, thorium-227 has a half-life of 18 days. If its initial count rate is 50 counts per second, what will its count rate be after 36 days? So this question has a lot of vocab, but is actually, I think, pretty simple. So I start out with an initial count rate of 50 counts per second. after one half-life, which is 18 days, I know that my count rate should be cut in half to 25 counts per second. And then after another 18 days, we're going to be cut in half again to 12.5 counts per second. Now I know then that 18 plus 18 is a total of 36 days. So what that means is that my count rate after 36 days is going to be 12.5 counts per second, since that's 2 half-lives. Another way I could solve this is I could say, okay, so I have 36 days, and there are 18 days in one half-life. So what that means is 36 days is 2 half-lives. And so then I would do the same thing. I would say, okay, so therefore I need to take 50 and I need to divide it in half twice, which again is the same thing as dividing it by 4, which again is going to give me that 12.5 counts per second, just like I got in using my first method. So you guys decide which of these two methods you prefer. Do you want to just look at chunks of time, half-life by half-life, or do you want to look at how many half-lives have elapsed and use that to figure things out? There are a lot of ways to solve these questions, but the key point here is that we are looking at half-life. We're looking at everything half-life by half-life. I want to also look at one more IB style example question. So what I'm going to do here is I'm going to use the graph below to determine the amount of isotope remaining after 100 seconds. So the challenge here is my graph stops at 50 seconds. So I'm having to extrapolate what happens all the way out here at 100 seconds. Thankfully, however, I can see I start with an activity of 2.8 seconds. So if I go down to 1.4, so that's when my activity is being cut in half, what that tells me is whatever time that's at, that is 1 half-life. So what this means is that 50 seconds is 1 half-life. So that means that 100 seconds is going to be 2 half-lives. And so my sample's activity should be cut in half again. So I'm going to take 1.4 and I'm going to divide that by 2, and I get 0.7 becquerels, or times 10 to the 22nd becquerels. Now, two things I want to point out. First of all, that times 10 to the 22nd. I got that by looking at the units on my graph. So just a reminder, as always, take a look at the units on your graph. It's not always going to just be in base units. Similarly, becquerels here are another unit for measuring activity. I'm just going to copy the same unit down that I saw on my graph. So I think that actually brings us to takeaways. So first of all, the half-life of an isotope is the time it takes for half of a sample to decay. Second, we saw in our graphs that isotopes decay exponentially. So after 1 half-life, half of my isotope has decayed. After 2, 3/4 have decayed. After 3, 7/8 of my isotope have decayed, and so on. Finally, we can use a graph of the activity or mass of, of a radioactive isotope to figure out what that half-life is. And we did that by looking at the initial amount of our sample and figuring out where on the graph we reached half of our initial amount of our sample. I think that's all I have for you. So with that, best of luck going forward and happy solving.